All right, so here I'm going to start going over some sample problem types that we could get with equilibrium. And keep in mind, I would say the hardest things about these problems is initially trying to figure out what type of a setup you have. And I'll give you guys a few hints here as I talk about each one. The very first type that we have is you're solving for one of the concentrations at equilibrium, singular, okay? Or you're looking for your equilibrium constant, which we talked about before as K, but a lot of times it's written as Kc. So the constant for equilibrium using concentrations, that's what the little c is for. And now here, an important thing is all the concentrations are already at equilibrium, so you could just plug it straight into one of these equations that we set up earlier with a quotient where you have products on top and then you have reactants down here on the bottom. So a few steps that you need. First of all, you need to have a balanced chemical equation. A lot of times it'll be given to you, but you might have to write your own and balance it. You also have to write your K expression, which is what we did up here. Q or K, it's the exact same equation. And then also you have to take whatever you have and then you have to plug it into the values here, and then you're going to solve for the unknown. Now the unknown might be a concentration, or the unknown might be the K or the equilibrium constant itself. Okay, so let's flip it over and look at the problem here. It says, given the equation, we have two of these bromine chlorides, and it's turning into bromine gas, and we also have chlorine gas that's getting produced. So here you have a chemical equation. It's all been written out, and if you're wondering why is the chemical equation important, it's because the coefficients that we have, they're going to become exponents when we write our expression. Okay, so here is our hint. We're being told that everything is already at equilibrium. When you guys see a problem like that, you should think yay, because it's a lot simpler if everything is already at equilibrium. The problem that we have down here, where you see this little chart, these are problems where they are not at equilibrium, so they require a lot more work. We have a 500 milliliter flask, and we have 4 moles of bromine, we have 2 moles of chlorine, and we're given the K, or the equilibrium constant for the reaction, it's 11, right? And earlier, remember how we talked about what the K means, right? If you have a K that, or the constant that's much bigger than 1, it means that at equilibrium, you have a lot more products that are getting made. If your K is less than 1, you have a lot more reactants that are getting made. So if you're looking at that here, we're looking for a singular concentration of bromine chloride. That's important because a lot of the other problems that you're going to see, they ask for multiple concentrations, and those are the ones where we have to set up these charts that you guys kind of see a preview of down below in the page. Okay, so let's go ahead and set this up. We know that our equilibrium expression, Kc, everything is at equilibrium, which is why I'm using K. It's the products divided by the reactants, so we have bromine times chloride. And I put the 2 here, that turns into an exponent because of the coefficient of 2. Okay, so we put all the products over here over on the top of our expression, and notice how it's a concentration of bromine times the concentration of chloride, and then we're squaring it again because that coefficient of 2. And you're going to divide this entire thing by the concentration of the reactants, which is the bromine chloride. And again, that coefficient of 2 means that that just becomes a square right there, okay? And we know a few things already. You know that the constant for the equilibrium constant, it's 11. So I'm going to just plug in 11 right here for that K. And we need the concentrations of bromine, chlorine, and then bromine chloride. And since everything is already at equilibrium, I could plug it straight in, right? But remember what concentration is always equal to. It's equal to how many moles you have divided by however many liters you have, okay? And for this, we have a 500 milliliter flask, and let's convert that straight over into liters. It's going to be 3 decimal places over to the left, so we know that this is a 0.500 liter flask, okay? If I have 4 moles of bromine and I'm dividing it by 0.5, so let's do that. We have 4 moles and we're dividing it by 0.5 liters. We get 8 molarity for bromine. We have 2 moles of chlorine, so I'm just going to do the same thing. I have 2 moles divided by 0.5 liters, and we get 4 molarity for the chlorine. And the concentration that we do not know is this guy right here, the bromine chloride. So let's go ahead and plug stuff in. The concentration of bromine, we determined up here it was 8. So we have 8 molarity times the concentration of chlorine, which we got 4, and it's 4 squared, 16, right? And we're going to divide this by the concentration of bromine chloride, which we don't know. And remember that it's not just x, but it's x squared. Okay, so if you went through and you simplified this out a little bit more, we would end up with 11x squared, and then we have 8 times 16, and we get 128. We're going to take 128, divide that by 11, and x squared is equal to 11.636. Okay, and to get x by itself, we just have to square root that. So if I square root this, I wound up with 3.4112, and I want to go back and check out how many sig figs I have, and it looks like the smallest number of sig figs I have is that guy right there. I have 1 sig fig, that's 3, that's also 3, so I need to round my answer to 1 sig fig. So we have 3 molarity here as a concentration of my bromine chloride. Not too bad, right? Now let's move this up a little bit, and we're going to look at sample problem type 2. And this one already, you could kind of look at the setup and think, oh, it's going to be a little more complicated. And this is what's given to you. You're going to be given not equilibrium concentrations, but look what they give you now. They give you initial concentration. So this is the stuff that you're starting with. They give you one concentration that is already at equilibrium. And what you're going to be asked to find is when they ask you to find all of your equilibrium concentrations, notice it's plural here, and you're also going to be asked to find the value of the K itself. And the KQ is also the same thing as KC. So they sometimes use KC to indicate that it's the constant for the concentrations, or the EQ to indicate that it's the equilibrium constant. So write an equation if necessary. You could tell that the problem that we did already had it written. This one down here already has it written for it as well. You're going to have to write our K equation, which we did earlier, up like that, right? So you do products over reactants with the coefficients turning into exponents. And then this time, we're going to be setting up something called an ICE table to calculate what the equilibrium concentrations are. Okay, so let's go ahead and take a look at what we have. We have our equation right here of sulfur trioxide, and it's breaking down into sulfur dioxide and oxygen gas. And we have that many moles of SO3, and it's placed into a 1 liter flask. Anytime you see a 1 liter flask, you should really like, because that means that the moles, this is equal to molarity, right? Because it's 2.5 moles divided by 1, so that just turns 2.51 molar SO3. And then see here, you stick the 2.5 moles into a 1 liter flask. This guy right here is your initial concentration. It's not how much you have after time passes and it's allowed to reach equilibrium. This is what you're starting with. And then it says at equilibrium, it's found that you have 1.88 moles of the SO3 that remains. And again, because it's a 1 liter flask, we could say that this is straight molarity. Okay, it says find the equilibrium concentrations. See how they ask for the plural concentrations, which is a good hint that you have to do a chart. And you want to look for the K constant, the equilibrium constant here. Okay, so there's a few ways that you could set up a table. This is one way. In another problem, I'll show you guys another way, which is just flipping it. But it's called the ICE table because you have initial concentration, then you have a change, and then you have equilibrium concentrations. Okay, so on the left side here, we just take the chemical equation that we had and we're going to just copy it down exactly. So 2 SO3, we have 2 SO2, and then 1 O2. Okay, and I like to draw a line between my reactants and products. So this is my reactant, those two guys are my products. Okay, so you have your table to start off with. So let's take a look at what we know. We know that we have 2.50 moles in a liter of SO3, and this is my initial concentration. So we're dealing with SO3, and it's an initial amount that I have. So it's going to be 2.50 molarity. And remember how we knew it was molarity? It's because it was moles over 1 liter. Now, we're told at equilibrium you have 1.88 molarity. About that, my little camera thing kind of fell down. Okay, so we're at here, it says at equilibrium it's found that 1.88 moles of the SO3 remains, and it's 1.88 molarity because we did moles over 1 liter. So here we know that we're dealing with the concentration at equilibrium because it says at equilibrium. So we're going to put the 1.88 right there. Okay, so if you take a look at all the numbers that we used 2.5, we used 1.88, and we're kind of done. We don't really have anything else to put into my chart here. So let's take a look at what we have. And I just want you guys to think about the initial amount that we have here. Okay, so the initial amount of SO3 is 2.5. And if they don't mention any of these guys here, it just means that you have 0 to start with. Okay, so initially I don't have anything, which is really common, right? You start with a reactant, you don't have any other products initially. You're being told 1 equilibrium concentration right here, so you could figure out the change that happened from 2.5 to get to 1.88. You could see that the change was negative because it went down. So I'm going to go 2.5 minus 1.88 on my calculator, and I got a change of 0.62. Okay, so 2.5 minus 0.62 is equal to 1.88. And I'm going to circle the numbers that they gave us because this is where we're getting that. Now, if you know the change for one thing, you could actually figure out the change for the other guys here. And one thing to note about the change is that you have coefficients from the actual equation, and the coefficients have to be applied for the change for you to actually know what the rest of the change is going to be here. So I'm going to go through and compare my coefficients. I had a 2 here, a 2 here, and I have a 1 here. Okay, if the coefficients are exactly the same, if it's 2 and 2, guess what? The change is also going to be the same. It's going to be 0.62. And then here, from 2 to 1, you could see that my coefficient halved. So I went from 2 to 1 over here. So guess what happens to my change? It's going to be half of this as well. Again, 2 to 1, so I'm going from 2 to 1 ratio. So this is going to be half of that. So you have 0.31. Okay? Now, I drew this line earlier on the problem here because I wanted to differentiate my reactants with my products. So if I'm looking here, if I see that my reactants actually went down, the products, it could only go up. So both of these guys here are going to have an increase in the products, and that's true for the entire side. So if I had 2 reactants, they would both go down, the products would both go up. And another really easy thing to know is if you're starting off with 0, you can't have negative amounts at equilibrium, right? So it could only go up. So that's positive and positive right here. So now, if you just do this, if you go 0 plus 0.62, you get 0.62 molarity. And 0 plus 0.31, you end up with 0.31 molarity right here. So now we know our equilibrium concentrations, okay? And we did all this work. We made a chart like this because this is what I wanted to know. I wanted to know my equilibrium concentration. So just like what we did up here, I could set up a K equation and plug in everything and solve for the unknown. Okay, so if you look down here, we did the hard part of the problem. It says find the equilibrium concentrations, and all the answers are here, here, and here. So my equilibrium concentration for SO3 was 1.88. My equilibrium concentration for SO2 is 0.62. My equilibrium concentration for O2 was 0.31. And all you have to do is set up a K equation. So it's SO2 squared, O2 divided by products, SO3 cubed. And all these numbers are going to go straight into the equation here. So SO2 is 0.62, square it. O2 is 0.31, and we're going to divide it by 1.88 cubed. And then you end up with your final answer. So let me just punch this out really fast, and you could do that as well. And we're going to get our final value of 0.01793. And here we have 3 sig figs, 1 liter, they don't actually give me a numerical value here, so I'm going to just ignore